Hello and good morning, everyone. How are y'all? Good? Sweet. Awesome. Let's get into it. Bond behavior and petrography of ultra-high performance concrete. My name is Kieran Weldon. I'm a senior at Virginia Military Institute. I worked in conjunction with Dr. D'Alessandro, Dr. Amnichanu, and Cadet Diagnu. He is a junior at VMI, and he was mainly responsible for the scanning electron microscope analysis. So the project overview, background information. So ultra-high performance concrete is not a readily available concrete product due to its high manufacturing cost and use of rare material, i.e. like quartz powder. So the goal of this research was to find a cost-effective means of developing a concrete mixture that met the criteria of UHPC, so 22,000 PSI. And it ranges, actually there was a discussion yesterday, between 120 to 150 megapascals, for those of you who are internationals. And the petrographic analysis was used to observe the effect of each mixing method on particle and fiber distributions, packing density of aggregate, and the mineralogy of aggregate. We're also going to get into the interfacial transition zone as well. So some of the materials/methods we used. Granted, this is a concrete mix that used a low amount of water and was incredibly heavy due to the use of steel fibers. So we had to use a vertical high shear orbital mixer, which presented its own complications. We essentially had to, a lot of the time we had to reverse it in order to cut through the concrete because it would end up pushing it around. We used a steam/submergence apparatus made using ovens and bowls and buckets of water. So every single day I would go down to the concrete lab and refill buckets of water in order to facilitate making a proper steam apparatus. So going on, we have the caps for our cylinders. So we ended up using 3x6 cylinders as opposed to 4x8s. The reason for this being we didn't have based on the orbital mixer, we didn't have a high amount of volume that we could work with, so we tried to cast as many samples as possible. These are the caps for 4x8 cylinders, and they actually have their own complications when using them with 3x6s, as you can imagine. And then we used a power saw actually to cut the surfaces of the samples, because when we originally cast them, they don't consolidate very well. A smooth surface is hard to achieve, so we had to cut off about 3/16 of an inch in order to facilitate proper breakage. We used a hydraulic press to test the compressive strength for the concrete. We used a vibrating table for consolidating each sample, and we used a standard micron thin section using high-pressured fluorescent epoxy impregnation. And we would put those under a polarizing light microscope and the SEM. So going on, here's the polarizing light microscope. So essentially we would capture an image using it, and then we'd upload it onto my professor's computer, and then we'd use ImageJ in order to, it's a free program online. We'd effectively put each sample into the binary mode to test to see how much aggregate was part of each sample. One of the problems that kind of came up with that, as you can see right there in the lower right corner, like I chose this image like on purpose for this purpose. We ended up finding that when we put the binary on, it has a certain threshold of light and dark mixtures, and some of our aggregates ended up being considered in the paste amount. So we're going to talk about ways to eliminate that later. And then we used a scanning electron microscope. Sorry, that's a typo. That's an image right there just showing some minerals and some voids. So part one, mixed design. We broke this project into two parts, mixed design development, and the second half is the petrographic analysis. So I started with a control mix developed by Colin Butler, a former VMI cadet. He actually presented at ACI last year. So I manipulated the water content of each batch, added silica fume to the later mixes. I wanted to get a good control mix at the beginning. And then I consolidated each sample using a vibrating table. I actually changed the types of samples based on what we were working with. So when I had like a higher volume, I would typically go to the 3x6 cylinders, but the 2x2 samples worked for the first mix, and nothing else beyond that. So, and I kept, I had some 4x8 cylinders, and there I wanted to keep for later evaluation, possibly of elastic modulus, that kind of thing. So tested various curing methods. So I actually went with a rather unique method of curing, steam curing. So going back to that apparatus that I created, submerged curing. So I actually kept concrete samples in buckets of water for 28 days straight. Once again, going down to the lab every time, refill that. It was a great feeling. And then I just used plastic covering in an ambient room temperature. So here's our original mix 1. We did 9 2x2 cubes, 4 submerged, 5 using plastic covering, 8 4x8 cylinders. We submerged each one for 5 days completely, and then we steamed for up to 23 days after that, but it says 28. So here's our mix design for that. We'll go into the 28-day break strength afterwards. Here's our next mix. This one actually presents an interesting problem when you don't dry your sand. So we ended up accidentally using wet sand and we decided to see where it goes. When you're making UHPC, it's all, you're working with so many materials that are based on the density of the paste itself. The steel itself actually ended up sinking down into each sample. And that's actually what inspired our petrographic analysis. But there was an unequal fiber distribution, as you can see, scaling on top of each sample. No tests were performed. We figured that those were, or any sort of compressive strength we got would be inadequate for the type of research we were conducting. So going on, here's our first mix with silica fume. 15 3x6 cylinders, all submerged as steamed. We had 1 4x8 cylinder for later testing. We actually used a 20% silica fume replacement. So we found a soupy consistency. The water itself was low, but it left behind residue. And that presented a ton of problems. However, the strength itself, as you'll see later on, could have been a lot higher. So going back to those caps that I was talking about earlier, made for the 4x8 cylinders, we attempted to break them using that because there wasn't a smooth surface. We figured we wouldn't get proper breakage. However, we found that there was a large amount of crushing, and that's a problem we fixed later on. But we figured the strength could be a lot higher. As you guys can see, there was frictional confining stress on both ends, and that's what kind of caused breakage in one end and no break throughout the cylinder. Silica fume mix 2. This is what happens when you don't use enough water. As you can tell, there's large voids. It was a very stiff mix to work with. Cut my hand a few times, to say the least. Not very fluid, very hard to mold. It did not consolidate using a vibrating table, which I found incredibly interesting. No tests were once again performed on this mix. Granted, the fact that large voids would completely offset the strength we were getting. So this is mix 3. Great mix, to be honest. However, thing about our concrete lab is it's in the middle of the mountain region of Southern Virginia. There's a little bit of humidity, so when you go to open up the cement bags, you got to sieve them properly because you're going to have clumps that are a result of the humidity. And that's what we had. So we ended up finding that cement clumps were present in each sample. As you can see in the samples there, we actually lubricated each sample using WD-40 on both ends, and that led to a complete shear break throughout. Once again, this is 3/16 of an inch shaved off each sample. This was kind of our inspiring moment to be like, okay, we need to break these properly. And we switched our superplasticizer from Sika to Lafarge because we actually found that Sika, you need a lot more. We were able to reduce our superplasticizer and our water by half using Lafarge. So going on, this is our silica fume mix 4. These are 6 3x6 cylinders, 1 4x8 cylinder. This time we actually took very careful and measured approaches of sieving the sanded cement. We had some voids present, but once again, we lubricated with WD-40 before the brakes. It was stiff, but it consolidated well, interestingly enough. So the water content was low, and evidently it was kind of like Play-Doh. It was great to work with, but it ended up consolidating once placed upon the vibrating table, which I found interesting. There's a possible repair application, so it stays in place. It would be great for looking at structures that are like 50 to 75 years old that need that extra set of strength. So here's our 28-day compressive strength. I'd like to point down to SF3 and SF4 mix. So SF3, as you can tell, there's a clear difference in the submerged/steam/plastic covering, and that's what led to SF4 having no plastic covering samples. We kind of made the determination that the submerged/steam apparatus was effectively able to get 28-day strength at like 7-8 days. We had 7-day brakes, braking the same as 28-day brakes. So it speeds up the process, but we found, however, that it's not necessarily the most effective in the long term. It's very great for achieving strength early. It's not very great for later. So we reached around 16,000 PSI at SF4. We kind of ran into some hiccups, at least in terms of the development stage. So it was nice to overcome that and get around to 16,000. We had some breaks that were even 18,000, but that's just the average number. Skipping over the slide, this is the petrographic analysis portion. Here is the image J analysis. So this is our standard image example. This is what I took off the AmScope microscope, the polarizing image. And then this is what we would take this and plug it into image J. This is another example from another mix. Currently, the petrographic analysis is actually still in research, so we're still looking over it now to get good numbers. We actually have some samples that haven't even gone off to get the epoxy resin. So we're still working on that. But this is the binary image example. As you can see, once again, in the lower left corner, or lower right corner for y'all, yeah, there's some problems with image J and the ability to do binary. So this is what I'm really interested in, the scanning electron microscope. This is Tim's work. This is the 800 magnification. This is all minerals and aggregate voids. Minerals, aggregates, and voids. This is the 1K magnification. So this is on the edge of a void, actually, and those flower-like structures there in the center are actually due to the epoxy resin of each standard thin section. And this is where I'm really interested. So the 3K magnification. So if you see that piece of aggregate over there to my left, y'all's right, it has a thin black line around it. That's the interfacial transition zone. It is significantly smaller than normal concrete. Normal concrete is usually 10 to 30 microns. This is sub-micron range. This could be due to a function of the silica fume as well as the low water content. Because of the low water content, essentially the aggregates would not have enough ability to saturate properly, and this is a great thing because it leads to less micro cracking in those regions as well, so higher strength. So recommendations in conclusion. So more data definitely needs to be gathered on making a more approachable mix. I mean, we used like low sand cement, standard like Portland cement, standard silica fume, but to achieve like 16.5 KSI is significant. However, it's still not UHPC range, so that needs to be developed and it needs to be repeatable. Finding the most ideal method to break cylinders prior to mixing is what I recommend. That was very, very, very difficult coming up because we could have probably gotten higher strength had we used WD-40 on the silica fume, one example. And then utilizing steam curing and submergence yielded the best results. However, is this practical in the field? So we were thinking in a perfect precast world we could, but on a site where we're mixing concrete, ready mix right there with a truck, very, very, very difficult to put things into a steam/submergence apparatus. So So what next? So further mixing, testing, and petrographic analysis is required in order to find and understand the most effective curing method in design. So we still have to work on that. So after determining the most ideal mix and the most effective curing method, bonding between the UHPC mix and our normal concrete mix will be used using, or will be tested using a push-off shear test. So we currently have at VMI 8 beam forms to go back and recreate based off Mr. Butler's research from last year. And we're going to be making those with normal concrete, purposely breaking portions of them and then adding onto our best, or adding our best mix onto that. So, and then seeing based on a push-off test how well that bonds. Here's our references. I'd like to acknowledge Takusan USA Incorporated for giving us our steel fiber, the VMI Center for Undergraduate Research, the faculty of the Civil and Environmental Department of VMI, and Dr. Richard E. Wires from Virginia Tech for actually suggesting to my professor to lubricate each sample. Thank you.